Let's talk about math flow diagrams. There are two methods that we discussed in class. The first one was earlier in the semester, and we referred to it as a phase variable math flow diagram method. And the second method is the Vannevar-Bush nested integration method. So I want to do two examples and kind of compare the two methods, show how to use both methods. One is kind of a refresher and the other one is newer. And then we're going to do some specific examples with the Vannevar-Bush as well. Okay. All right. So let's look at a system that, let's give this system equation something like a second order, and we'll just do something simple. A U of t plus a disturbance term. And this is our system. So it's a second order equation, has a control input and also a disturbance in it. Okay, so if we wanted to do the phase variable method, remember, the first thing we would want to do is get the equation in such a form that we had the highest derivative of the output on the left-hand side. And then everything else, no matter what it is, even if it is a derivative as well, even if we had a y dot term, we'd still want it to be over here on the right-hand side. So we just want to isolate that y double dot term. So the way that the way we've written this already, and by nature of the system that we're working with in the example, it just turns out that it's already in a good form for us to use for this method. Okay, so the first thing we'd want to do is start drawing our math flow diagram. Now, the way I like to do it and the way that I taught in class is to take this variable and go ahead and draw that right there and label that. And then what you can do is add on the integrators, and don't forget the initial conditions. Label again, and keep going until you get the system output y of t. So here, after two integrations, two integrator blocks, we get a y of t. Okay. So now the problem is to build this y double dot signal. And our equation is already set up to do that. We know it has two components, which we need this summation block that I just drew. Okay, these are both added in. I'm going to choose to have u of t come in from the side and the disturbance come in from the top. So we've got this right here. So we'll have disturbance coming in here. I'm just going to choose to represent it with a box. I didn't give any additional information in this problem for the u of t or the disturbance term, and we didn't design a u of t here. If we did, we could just plug it in. But let's leave that as a box for this example. Okay. This is actually our completed phase variable method math flow diagram. Okay, so over here, let's use the Vannevar-Bush method. So I'm going to rewrite that equation. Y of t equals u of t plus w of t. Both methods are not domain specific. You can use them in the time domain, or you could use them in the Laplace domain if you happen to be working that way. Okay, so we are using the Vannevar-Bush nested integration method. Okay, so the first step here is to start with an equation in the form of derivatives on the left-hand side and then everything else that's not a derivative on the right-hand side. Once we have that, which we actually already do have that form, we would integrate and integrate both sides, but integrate them differently. Integrate the left-hand side piece by piece. So if we had like a y dot term added in here as well, we would integrate each individually. But on the right-hand side, we integrate everything as a single unit. It all gets one integration and it all gets paired together. So let's show that. So if we have the integration step and I symbolize it like that, we now have a y single dot on the left-hand side, and our integration on the right-hand side is all together, just like this. Okay, we're not done yet. We can't draw our math flow diagram yet because we still have a derivative term on the left-hand side. So after this step, normally our step would be to refactor, put everything that's not a derivative over here on the right-hand side, and then to reintegrate. We actually don't have anything to move, so let's go ahead and reintegrate. So we have y of t equals another integral, and then u of t plus w of t stays. We have the dt from that first integral, and then the dt, and you may choose to use a d tau or something to make it different than the first dt, and that's fine. But I'm going to go ahead and use brackets and set it apart. Maybe that wasn't a good choice because it is kind of blending together, but we have two integrals, and this is the nested bit right here. Okay, so we can actually stop with the equation at this point, and we are ready to draw the math flow diagram. So the way you do this is you look at the left-hand side, and then you work towards the right, and on the diagram, you work towards the left. Start with the output, y of t, and as we work rightward, the first piece that we encounter is this integrator. So we draw an integrator moving this way. Put in the initial conditions, and then it has an input. As we move again towards the right, we see we have another integrator. Okay. And as we move towards right, we can see that we have two pieces that are added together in the nested part. So we need a summation block. Let's do the same style that we did over here. Have two imports coming in just like that, and then we have the disturbance on the top, the block format, and we'll say that the control signal comes in from the left-hand side. Okay, so as we look at this, for this specific example, the two math flow diagrams look exactly alike, and indeed if we were to label y dot and y double dot here, they are exactly alike. We have the same access to all of the signals, and all the state variables for each line are the same. Each line is the same. Okay, but this is not always the case. Let's do another example, how we can see the structure changes. And in this second example, let's say we have a third order system. We'll have a y triple dot minus 4y double dot plus 5y single dot minus 10 times y equals u. And I am specifically choosing examples that we can use both techniques with here. And you may be thinking, well, there are some times when you have to use Vannevar Bush, and that's true. And that is the case when you have input derivatives, and we'll do examples like that next, and we can only use the Vannevar Bush nested integration technique for those. But we'll do one more where we can use both methods. So for this system, let's try the phase variable method first. And so I'm just going to use this space right here to move the equation into the appropriate form. Okay, so for the phase variable method, and then we'll have Vannevar bush over here. Okay, for a phase variable, remember our method was to get the highest derivative of the output on the left-hand side and then move everything else onto right-hand side. So let's do that. Y triple dot equals 4y double dot minus 5y single dot plus 10 times y plus u of t. Okay, so we are now in a form where we can draw the phase variable math flow diagram. So let's do that. Okay, the phase variable math flow diagram will look like this. Let's first draw the y triple dot line. That's what we start out with. And now you may choose to go ahead and put in the integrators to produce the y. I'm going to go ahead and choose to do that. We'll take 3 integrators to produce y. And I should have made this a little bit longer. Oh well. Now let's go back, put in our initial conditions, and I'm just going to bubble up here that we're going to put initial conditions in all 3 of these integrators. The other thing I want to do is go ahead and label these lines just in case we're going to need them. It turns out we will need them here. So y, let's see, y double dot, y single dot, and then we've got our y right here. Okay, so back to our equation here. We want to figure out how to produce this y triple dot. I know that it has these 4 components to it, so I'm going to need a summation block here. And you can choose to split this up and make a summation going into a summation and such, but I'm going to use one here because it's very obvious how this works. So let's choose, since the y double dot is closest to the summation, let's go ahead and choose that one to be closest in the inner loop here. So let's add that, and we're going to need a gain of 4. I'm going to connect that up. And don't be afraid to label lines. I know I've said this many times, but it really can help you out. It can help you debug and figure out what you're missing and such. Here we have a y single dot, and we're going to have a -5 as a gain. I'm going to put the -5 in the gain. Usually I put it on the summation block, but you can always do whatever you like as long as it's accurate. Okay. And, oh, whoops, yeah, almost did that. Force of habit. Okay, -5 times y dot right here. Okay, and we've got one more term, that's the 10 times y. Okay, so I'm going to add that and just connect up our feedback here, and we will have a 10 gain, and then I'm going to label that because that is 10 times y. Alright, we are missing just one piece, and that is the u of t. We envisioned that in our first example was just a block input. So I'm going to do the same thing here. And again, if we had designed u of t, we could plug it in. I really like drawing the plant out like this and leaving a space for u of t. So if we had already designed this, it would be good to just go ahead and have this part connected up just like this, label this line, have this all existing as it is, and then draw in the u of t. That way, all of your system is visible, and then your control is separate as well. And that makes it easy to debug things. So, I'm going to draw this line over here, and then we'll continue with the Vannevar bush technique. Okay, so back to our original system equation right here. For the Vannevar bush technique, I want to start in a very different place than we started with phase variable. I want all of my derivatives on the left-hand side, everything else on the right-hand side. So that means that I'm going to have 3 terms, y triple dot minus 4y double dot plus 5y single dot on the left-hand side. And then I'm going to have this 10y moved over to the right-hand side with the u of t. So once we're at this point right here, we're ready to start our integration and start building those nested integrals. So let's start our first integration, and that's going to leave us with a y double dot minus 4y dot plus 5y. Now I'm integrating term by term here, okay? But over here on the left-hand side, we integrate as the unit. So it all belongs into this integral right here. Okay, so now you can see that I have one term as a result of this equation that is not a derivative. I've got to move that over to the right-hand side before I can continue. So let's do that. Y double dot remains minus 4y dot. That remains as well. We move over the 5. Be sure not to put this in the integral, and it's also not really a good idea to put it after the integral because it can be confusing. I always like to put it before the integral. That way it stands out a little bit, and there's no risk of accidentally grouping it in a following equation. Okay. So we've got this, we can go ahead and integrate. So we integrate again. We've got y single dot now, following from the line above. And then we have a minus, and that's going to be a, let's see, that's a 4. 4 times y equals, we have an integral over here. I'm going to use a larger parenthesis, minus 5y plus integral of 10y plus u of t dt, and then the dt on the outside here. Okay, so once again, we're just going to go ahead and refactor, and then we'll repeat that same procedure. So rewriting, we have a y dot equals 4y plus integral of negative 5y plus, and I'm just copying directly, I haven't changed anything for this part, just like the line above. Okay, now let's integrate. Okay, integrating, we result in a y here on the left-hand side, and then I'm going to draw the integral and put in brackets to make it stand out. We have a 4y, just copying this inner part from the line above, another integral, negative 5y, plus integral 10y plus u of t, close that out, dt, close out that second parenthesis, another dt, close out the bracket, and that has a dt, which we can just squeeze in there. All right, so we have no more derivatives on the left-hand side. We can now draw our math flow diagram. And this is all of our nested portion over here on the right-hand side. Okay, so what we want to do is start with our output, and we're going to again work rightward, and on the diagram work leftward, kind of like we did when we started at this point right here. We did fill in these integrators, but then we started working towards the left on the diagram. So kind of a similar idea. So we start that y of t, and then as we move rightward, the first thing we can we come across is this integrator block. Draw in the integrator block and add in the initial conditions if we have them. Okay, continuing on, we go into the nested part. All right, so we have two components that are getting added together, and that is the 4y and this integral. So we need a summation block. I'm going to put the 4y on the bottom, and that gets added in. So we have, this also has a positive sign, so we have two positive signs, and a gain of 4. Go ahead and connect that over to the y. And then and this should be for y once it gets added into the summation. Alright, so this right here has an integral, so I'm going to need to continue on. Put that there. And we can see that our diagrams are now starting to look completely different. Okay, and indeed for this example, they are going to look very different. Okay, so initial conditions come in here. We have inside this integral, this is where we're looking now, we have a -5y coming in, and that gets added with this integral part right here. So we need another summation block. I'm going to put the negative sign on the summation, and then we have a positive sign for this integral. Okay, so I'm going to connect this around. This is a -5 gain, so we'll have a negative, oh, whoops, put the -5 up there. Whoops, did that again. All right, connect that up to the y. And this should be 5y, and then it gets subtracted off to make that negative sign. So this should work. This is all good right here. And it's always a good idea to check yourself sometimes. And then we have this integral right here. So add in the integrator, if we have any initial conditions, of course. Now we have inside the integral a 10y and a u of t. So again, I need a summation block. Now, because I put my line here, I'm going to have the u of t coming in from the top, just so I don't have to cross the line right there. And then I have the 10y, and I'm going to have that coming in from the bottom, just as we've done before. Okay, so connect that down. This should be 10y on this line. So I'm going to need a gain of 10. Draw in our gain block and then connect it up to the y. All right, and this is our completed math flow diagram done with the Vannevar Bush technique. So we can see phase variable, math flow diagram, and our Vannevar Bush math flow diagram. So you can see how different they are. One thing I want to point out is they both have 3 integrators. This is a third order system, and if we look back at our last example, we had a second order system and 2 integrators over here, 2 integrators over here. These math flow diagrams were the same, but still second order system and 2 integrators. So in general, you should always have the same number for your plant, at least, and that's what we're plotting, or what we're diagramming. The plant number of integrators equal to plant system order. So if I have a third order system, I should have 3 integrators in each case. That does not take into account the controller. You may put extra integrators in your controller for whatever reason, especially if you have a disturbance or something like that that you need to take care of. So, but just the plant portion, this is the minimal order design. Okay. All right, so we have, let's just concentrate on Vannevar Bush, and let's do 2 examples where we would have to use Vannevar Bush. So again, when do we have to use Vannevar Bush? And that is for math flow diagrams. Well, it's whenever you have a case of input derivatives. Okay, so when these are present, you'll have to use Vannevar Bush to deal with them. All right, so let's do an example, our first one. Let's say we have a transfer function now. So I'm going to add in a little bit of complexity here. We're going to have a transfer function, and we're going to pull it out of transfer function format into time domain format, and then we're going to do the math flow diagram from that. So just to get that little bit of extra practice. Because with transfer functions, that is a case where we often see input derivatives. Okay, so let's say we have this G1 transfer function, and I have this numerator here and this denominator given here. Now, remember from Laplace that a multiplication of an s is going to be a derivative. A division by an s is an integration step. And also remember that a transfer function in general is a ratio that is output over input. This can be a component or it could be the entire system. Here I want to look at a component. So I'm going to say that I have this block called G1 in the S domain, and it has this output, and we'll call the output Y1. We'll call the input U1, but we could use any variable that makes sense to use. Again, you'd want to avoid things that are obviously bad, like using an S or something like that. That's just a bad label because we're in Laplace domain, but whatever makes sense. Okay, so let's multiply this. So output Y1, input U1. All right, so I'm going to multiply this out, and so we have the 2s minus 10 times the U1 and that is equal to the s squared minus 2s minus 10 times the y1. Okay, so let's go ahead and expand this out. We have 2s u1 minus 10 u1, and after this line I want to swap these two. S squared y1 minus 2 s y1 minus 10 y1. Okay, so now I really want the y to be over here so we can follow that y equals blah 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 type of format. So all I'm doing in this step is swapping these two sides. Okay, there we go. So now, in this next step, what I want to do is go from the Laplace domain back to the time domain. So my step is to take the inverse Laplace, essentially. But really, it's much simpler than looking it up in a table, even. Multiplication of an s, remember, is a derivative, so that's really all I need to know since we're holding initial conditions at 0. Because of that, we don't have anything else to factor into this equation. So we have a y1 double dot minus a 2y1 single dot minus a 10y1, and then set that equal to 2 times u1 derivative minus a 10 times u1. Okay. So this right here is the equation that we can start using the Vannevar technique with. We're in the time domain here, and we are all set up and ready to go. So let's get our derivatives on the left-hand side, everything else on the right-hand side. Okay, y double dot 1 can remain, minus 2 y single dot 1 can also remain. This one has to be moved over to the right-hand side, but I'm going to take this to u1 over here. Okay, and then moving this one over, 10y1, and then we have a minus 10u1 that stays over on the right-hand side. Okay, we're ready to go with Vannevar. Let's go ahead and do our first step, which would be the integration. Okay, so integrating this equation right here, we have y1 single dot minus a 2y1, no dots remain, 2u1, no dots remain, and then integrating this entire side on the right hand side, just like so. Okay, so let's refactor, move these two terms over here. Okay, so that's a positive now, and this one also is positive. And then we add in that integral 10y1 minus 10u1 dt. All right, we are now set up so that we can once again integrate. So let's do that. So integrating, we have y1 equals everything else in the left-hand side is going to be inside this integral. y1, 2y1 plus 2u1 plus integral of 10y1 minus 10u1 dt, close bracket, dt. Okay, so we are now in the nested equation form. And that is where we can stop and start drawing our math flow diagram. We can stop doing the integration and all of that. So, and get ready to go. All right, so let's try this out. We have y1 of t. Okay, as we move rightward, we have an integration block, initial conditions if we have them. And the input to this integration block has 3 components. I can see that I've got the 2y1, the 2u1, and then this integration part right here. So I need a summation block. I'm going to put the 2y1 on the bottom because that's most convenient for the feedback. Connect that up, label it 2y1. We've got 2u1. Now the u1 comes in a different place. I think it would probably look good to put it in at the top here. So let's add that in. We'll put in a little gain here with a 2 in it, and I will put u1 as a source right up here. So if I need it later, which I should, I will be able to access this line. Okay, and then this third component is the integral. And initial conditions come in. Okay, so inside the integral now, this is our last part for this problem, we have a 10y1 minus a 10u1. Okay, so let's take the 10y1 and put that on the bottom. So I'm going to have a gain of 10, and then I'm going to come around here and connect up that y1. And then I should have 10y1 coming in right here. Our next part is the negative 10u1. So now it's good that we put this here because we have easy access to the u1 signal, and we can just easily send that through a negative 10 gain, and that gets added. Okay, and this is our completed math flow diagram for the Vannevar technique. All right, so let's do that real quick check on the integrator count. We have 2 integrators, and if we were to look back at our original system, let's look first at the time domain. We have a second order system. Look at with respect to our output. Our output should be either equal to the input derivatives, or it will be greater than. So that's the one to examine. Or if you want to look back at the transfer function, the polynomial on the bottom, that's the order we want to look at, and that is squared. So that's a second order system, and we have 2 integrators in place. So looks good, checks out. All right, so let's do one more example of the Vannevar technique. Okay, and we'll again start off with a transfer function just so we can get that extra practice. In this case, I'm going to use a g2 of s equal to 10s squared minus 4 over s squared. Okay, if we recall that this is again output over input, I'm going to say our output is y. I didn't like carrying through the subscript in the last one, so I'm just going to use y and u for this one. Okay, and that means that for this block, this G2 of S block, the output is the y and the input is the u. Again, for compensator blocks that we design, our output is actually u, so your ratio will have different variables than this one. Okay, so let's cross multiply, and we have a 10s squared minus 4 times u equals s squared times y. Take the inverse plus, and we can, and also I'm going to distribute this at the same time. And so we will have a 10u double dot minus 4u equals y double dot. And again, I'm going to swap those just so we have it in the correct form here. Having the output on the left-hand side is much better, I think. Okay, so this is our system equation that we're going to start with and build our nested integration off of. So we need to move this derivative right here over to the left-hand side. So we've got y double dot minus 10u double dot equals negative 4u. Okay, we are set up to do our first integration. Let's do that. Y dot minus 10u dot equals integration of negative 4 u of t dt. Okay, there's actually nothing left to do as far as refactoring. We just integrate one more time. And we have y minus 10u equals integrator negative 4u of t dt. And then we have the other dt for this other integral. All right, so let's get it into y equals format by moving that negative 10 over 10u of t plus integral negative 4u of t dt dt. Okay. All right, so what we have here, we are ready to go with the math flow diagram. Let's start with our output. Our output is going to be y. So we have y of t. And as we move rightward, first thing we encounter is two components that are being added together. So the first thing we need is actually a summation block. Let's again have our u of t be a source that's supplied from the top. That'll be really handy. And then we'll have our 10 gain. Gets added in there. Okay. The other part is this double integral, and you can see this actually has a negative sign because it has a single component. I'm just going to go ahead and put that negative sign right on the summation block. All right, next two pieces are two integrators. Okay, if we have initial conditions, they will apply. Okay, so that'll apply to both of these, just separating their initial conditions. And then what goes into the second integral, this nested bit right here, we already took care of the negative sign, so I'm not worried about that. But we need a gain of 4 multiplied by this u of t signal. Okay, and then just connect that around. And so this is 4u of t. All right, and that is our completed Vannevar Bush math flow diagram. Again, this is a simple example, but it gives you an idea of the technique and how to build these up. And also the differences between the phase variable technique and the Vannevar Bush technique.